Dejamos la puerta abierta, ¿quieres que la cerremos?
Como hay un micro, yo no puedo estar abierta.
Sí, ¿verdad?
So we start with this session. Thank you, everybody, for coming. I see the room that is packed of people, especially young people. That is especially the object of this talk here. Okay. So what I would say, we are so happy and so honored that Anne-Lulier is here with us. Okay, that almost is not necessary to read to you which is her merits of in the CV or something like that. And nevertheless, I will tell you something about that, a little thing, a little thing about that. So Anne-Lulier, well, she's very well known as an experimentalist, but she is also a very good theoretician. And in fact, she began her scientific career as a theoretician with a master in physics and mathematics in the École Normale. Okay, then he went to the Commissariat of the Department of Atomic Energy to make her thesis, her doctoral thesis, and this was a completely changed because he began to do experimental work there. Okay, at that time there were lasers, intense lasers were beginning to grow. So she was joining a group in doing some experiments in photoionization of electrons, okay, with a very known group there. It was the group of Michel Ferrer, no, sorry, Gerard Manfred, okay, and she joined the group also of Michel Ferrer and Louis-André Lompré, okay. So she made these studies in ionization, and then after this, as a postdoc, then she began to study the emission of photons from atoms subjected to very intense laser fields. And from this early work as a postdoc, began the whole story of attosecond physics, okay? Because she was the one who understood and found that the atoms could emit radiation in very high frequencies, okay? This is what we call high harmonic emission, okay? And this was one of the main results that finally led to the way to the attosecond physics, to the field of attosecond physics that she will explain to us. So after this stay in the Commissariat in Sierre, she went to Lund then to join the University of Lund. After that, she was already doing a lot of interesting work and very fundamental work in harmonic generation. For instance, she was the first to generate harmonics up to the order 100, okay? And okay, and after from that, she has just developed an outstanding career in the experimental and theoretical description of the process of harmonic generation and attosecond pulse emission. Okay, so let me end with some of the prizes that she got during her life. She has the prize of the Prix Saint-Coton, the Goran Gustafsson Prize, the UNESCO L'Oréal Prize for Women in Science, the Bose Prize, the VVA Prize, that is the Banco de Bilbao Vizcaya Prize, okay, Leibniz Zukunft Prize, academic, and she's the academic member of the French Academy of Science. And finally, of course, she got the Nobel Prize in 2023. Okay, so without saying much more, I can tell you that the people that we know from her, either for collaborating or either because we have seen her career during all these years, we can say that she is an outstanding scientist. And I would say that she is honest. She's known for the honesty and the humble way that she approaches to physics. So in fact, for us, and for the young people, and also for the older people, I think it has been always an inspiration, the way of doing this kind of work. So, without much ado, I think I will give place to Anne.
Thank you very much. It was a great introduction. So I'm very happy to be here in Salamanca. It has been a fantastic day. This is just to introduce the subject a little bit. It's called an arrow of time, and it's several orders of magnitude of time, starting by the age of the universe, which is about 10 to 18 seconds, down to the attosecond, which is 10 to minus 18 seconds. So you have astronomical time, humanity time, and then the second, the heartbeat, millisecond. This is time for mechanical motion, electronic motion, nanosecond. Femtosecond is the time for atoms to move in molecules, and it was the field of femtochemistry was awarded a Nobel Prize in chemistry in 1999 to Ahmed Zivan. And then attosecond is the time scale for electrons to move in atoms and matter in general, and led to a Nobel Prize 2 years ago to Pierre Agostini, Ferencross, and myself. So this talk is a little bit the story of this Nobel Prize. Where do these very short light pulses come from? So this is the outline of the talk. First, I'm going to talk about high-order harmonics. Then I will talk about attosecond light pulses, and then a little bit about application, with very fundamental application to study electron dynamics. What do we mean by that? So let me start by saying that nothing of what I'm going to tell you would have happened without the invention of the laser in 1960 by Theodor Meinmann. And we are going to use two properties of laser light in our research. First, the fact that you can confine laser light in pulses, and second, maybe most important, that it's intense light. So the invention of lasers opened new field of research immediately. And immediately you have the beginning of nonlinear optics, with here the invention of discovery of second harmonic generation in a crystal by Peter Franken in 1961. So you have here a picture of the experimental setup. You have a laser which you focus into a piece of quartz, and then you analyze the radiation with a prism. And they saw two points corresponding to the fundamental light and to the second harmonic. So nonlinear optics, new frequencies. The other field that started thanks to the invention of the laser is very fundamental studies of atoms in strong laser fields. Multi-photon processes, the fact that atoms can absorb several photons. And it's interesting to note that multi-photon excitation process, as this one here, it's the two-photon excitation process. This was predicted theoretically in 1931 by Maria Goppert-Mayer as an exercise in the new quantum mechanics. So I like this very much. In the 60s, Russian scientists develop lasers and use these lasers to ionize atoms by multiphoton absorption. So this is called multiphoton ionization. In 1979, Pierre Agostini and his group discovered what is called above threshold ionization, where an atom can absorb more photons than what is needed for the ionization. Here, one more photon. This is called above threshold ionization. And he discovered these processes by looking not only at the ions that were emitted, but at the electrons and which energies that the electrons had. And my own thesis work, this was beginning of the 80s, a long time ago, was to study multiple ionization processes by multiphoton absorption. For example, here, creation of doubly charged xenon atoms. At that point, we had the intuition, the knowledge that, okay, it's easy for an atom to absorb all these photons. Probably we also create excited ions or excited atoms. Would be interesting to know more about these excited species by looking at the light emitted by these excited ions when they decay. So it's fluorescent light. So we set up an experiment looking like this. We send an intense laser into a gas, focused into a gas, and we look at the radiation that is emitted using a grating to analyze the radiation. So this is a picture of the laser that we used at the time. It's picosecond, and it's 10 Hertz repetition rate, neodymium YAG. The people working with the lasers here, I hope they agree that this is rather old laser system. The lasers don't look like that anymore. But you can see, this is where the oscillator is. You have two mirrors here, and then amplifiers. This is a picture of the experimental setup. The laser is coming from the right, and what you have is a vacuum chamber. And inside the lens is here, and inside you have gratings. So we were actually not only looking at the propagation direction, but also perpendicular directions. We were really looking at fluorescence. There is an arm here looking at the perpendicular direction. So here you have the grating and detector. You can notice that we have a printer here. This is really the time before personal computers, and we were taking data using this printer. It was a rotating printer wheel, and the pen was linked to our detector, and we were rotating a grating, and we follow the signal like this, just the pen moving. What did we see? Well, we did not see fluorescent light. This is the beauty when experimental physics bring new result, unexpected result. What we saw was high order harmonics of the laser light. You have here an example of a spectrum obtained in argon gas showing odd orders up to order 31. Why odd orders? This is due to the symmetry of the interaction, which is a symmetry relative to the origin, and this kills the even orders. If you plot the distribution of these harmonics, you get this characteristic behavior with a plateau, first decrease, plateau, and then a cutoff. And I would like to say that the discovery of this result was really this plateau behavior, because at the time we were thinking very much in terms of perturbation theory to describe the interaction between light and matter. And you would like to extend the polarization induced in the medium by the laser light. as a series of powers of the electric field. For such an expansion to be valid, you need this first term here to be much larger than the third, much larger than the fifth, and this was not the case. We had this plateau behavior. So it's a non-perturbative behavior. So very highly nonlinear and non-perturbative. Very exciting. To understand high-order harmonic generation, you need to do some atomic physics or quantum mechanics. You need to describe the interaction between atoms and the laser light. And this is described by a Schrödinger equation with, here you have the atomic potential, of course, and then you have the light-matter interaction, which can be described in the dipole approximation using classical field. And this is what you have here. The difficulty in solving this equation is that this light-matter interaction is strong. It's almost comparable to the atomic potential. So you cannot use perturbation theory, for example. And the first attempt to solve this problem was to solve the Schrödinger equation numerically. But you also need to consider the response of the medium to the interaction in order to have to generate efficiently high-order harmonics. You need a certain phase matching condition to be achieved. You need the emission of the waves by the atoms to be in phase in order to build up the harmonic field. This is traditionally described by Maxwell's equation, which can be simplified to a wave equation, as you see here, with a generated field here, depending on the medium polarization, which is obtained by solving the Schrödinger equation. And again, the first attempt to really simulate this problem was to do it numerically. With good success, however, we did not really understand the physics behind. This would come later. I'm moving a little bit in time. So this happened in 1980, 87, 88. At that time, I was a young researcher in France at the Commissariat Énergies Atomiques. Now we are at the beginning of the 90s. Huge progress in laser technology. Progress towards shorter pulses and new laser material called titanium sapphire. New technique to generate femtosecond pulses from an oscillator. And also new technique to amplify short pulses, which is called the Chubb pulse amplification, and that led to a Nobel Prize in physics to Gérard Mourou and Donna Strickland in 2018. In Sweden, in Lund, they use two scientists here, Sune Sandberg, Claes-Göran Barström, they use this new technology to build a new laser facility using these different inventions, laser inventions. So they build the first terawatt laser system based on this technology in Europe. And later on, this will really spread out in Europe, especially here in Salamanca, actually, as well. At the same time, back in Saclay, we are developing dedicated instrumentation to study these high-order harmonics. And here you have a picture of the setup that we use. So this is me a long time ago. This is my first PhD student, Philippe Balcou, in France. And we built this instrument that you see here. We don't see the laser here, it's behind the wall. So what you see is vacuum chambers. This harmonic radiation is in the extreme ultraviolet range. It's absorbed in air, so we need to be in vacuum. So what you see here are vacuum chambers. And in the first chamber, you have the gas jet. Then here you have some optics to analyze the radiation. And finally, a photon detector. In this case, is an electron multiplier. It's here. So we built this instrument, and we used a laser that we had at that time, was a neodymium glass laser. The Chirpers amplification was implemented, so we had short pulses, however, horrible repetition rate, 0.1 hertz. So it was a little tough to do experiments. This was also the time where European collaboration started, networks, and then later it would be Laser Lab Europe, where European teams started to collaborate with each other. And we were asked by the people in Sweden if we would be interested to come with this instrument and using their laser system, and brand new. And this is what we did. So the specification of this laser were 200 femtosecond, 10 hertz repetition rate. So you see the difference. 100 more laser shots. And this is an example of results that we obtained. This was in 1993. In helium, you see that beautiful harmonics. The cutoff is around the 93rd harmonic, so much higher orders. And also a fantastic plateau, extending actually to much lower orders. I'm coming to the second part of this talk, attosecond light pulse. I'm looking at the young people here. You follow me? Yes? Yes. Okay. The idea of attosecond pulses was proposed, you see here, in 92, 93, just a few years after the discovery of the high-order harmonics. And it's presented here on this cartoon. So what you have here is 3 harmonics, 17, 19, 21. Let's assume that these 3 harmonics are phase-locked, which means that they are in phase at a certain time. So for example, here they are in phase at this time, the maxima coincide, and then the minima coincide, maxima coincide, etc. And this happens every laser, half laser period. If we sum these 3 harmonics, what do we get? We get a series, we call that a train, of short light pulses, simply because of interferences. When these 3 harmonics are in phase, they add constructively, while they are not in phase, they add destructively. So through this interference mechanism, you concentrate light into short time intervals. And just looking at the numbers here, we are in the range of a few hundred of attosecond. What is shown here is the intensity of this attosecond light pulse. If we add not only 3 harmonics, but let's say 10 harmonics, you have the possibility to get even shorter light pulses. So this was very exciting. The reason why we get these very short pulses, possibly, was that we are talking about light with high frequency. We are in this extreme ultraviolet regime with high frequency, so short optical period. We have a broad bandwidth due to this plateau of many high-order harmonics with the same intensity, so very broad bandwidths. But the question was, are the harmonics phase-locked? Is this hypothesis true or reasonably true? And actually, it is going to take the community in total 14 years to go from the high order harmonics to the attosecond light pulse measured in the laboratory. It took some time to understand it, and then later to come up with a method to measure attosecond light pulses. There was a huge breakthrough in 1993 in the theoretical understanding of the single atom response, which was due to the people that you see on this slide. This model, it's called the three-step model, is illustrated on this cartoon. So I'm going to tell you what this model tells us, and then I'm going a little bit later to do an analogy. Okay, so I'm mostly talking to the students now, to the young people. So I start by the physics, which is presented by this model. So what you see here is the atomic potential. It's a Coulomb potential, looking like this, with symmetry, the revolution symmetry. Because of the interaction with the laser, this potential is bent on one side, and this leading to one wall of the potential going up, the other going down. So suddenly we have a potential barrier here. We are in the macrocosmos, in quantum mechanics. There is a certain probability for an electron in the ground state to tunnel through this barrier. Then the electron is driven away by the laser, few nanometers. When the laser changes sign, the electron is driven back to the nucleus, and then there is a certain probability for recombination. And in this process, there is emission of XUV radiation. So this was a physics description. So now I present that a little bit differently, and this is called an adventure of an electron in the laser field. So you have, this is in Swedish, by the way. Very easy, you put K instead of C. Okay, I can represent this situation that you have here this way. Okay, you have an electron in a prison. This is a strong force between the electron and the nucleus. It's great, otherwise we would not exist, okay? So the electron is very stable. It's in prison. But then on the side you have a huge roller coaster. I don't know how it's called in Spanish. You understand what I'm saying? Yes. So the electron would like to have fun, of course. What does the electron do? You have to help me here. What does the electron do? He jumps, he would like to jump on the roller coaster. How does he manage to do that? He escapes from prison. How? So I see this thing here. No. Yes, he tunnels out, of course. This is what he's doing. Yes. So the story continues on the next slide. And this is this. The electron is very happy, is going up and down in this roller coaster. It's like going in the laser field. This analogy here is with gravitation, but it's similar. The story is finishing very bad. And this is the end of the adventure of the electron. The electron is meeting on his way the open prison, and is falling and is screaming out his energy. And this is our attosecond light pulse. End of the story. Okay. Okay, now I would like to connect this picture with the high harmonics and with the plateau. So here we have a picture of the interaction in the time domain. So every half laser period, you have the escape of an electron. So you have a possibility for different electron trajectories, and the electron comes back, actually not exactly at the same time, with a certain spread in time, and with different energy. And this is making our attosecond light pulse. Okay, we can think of an electron wave packet, and then attosecond pulse is emitted. So in the frequency domain, so now I'm going from time to frequency. This corresponds to a broad plateau. So here we have a plateau. The plateau is in the time domain, this is this short light pulse. Now this process is repeated on the other side of the atom after half a laser period. So you have again the emission of an attosecond light pulse with actually a spin flip. And now if you go in the frequency domain, you obtain a modulation of the spectrum with frequency 2 omega. It's just Fourier transforms, just mathematics actually. And this is repeated several times, depending on how long your laser pulse is. And this interference spectrum become sharper. This is the same mathematics as diffraction through multiple slits, leading to interference in the far field. Here, our slits are not spatially, they are in time. So this is temporal slits leading to interference in the frequency domain. And this is our high order harmonics. So now we have an understanding from in the temporal domain, which allows us to, first of all, to predict the existence of the attosecond pulse, and then to explain the generation of the high order harmonics. I would like to say a few words about the second aspect of this problem, which is phase matching. How does it work? Well, first, what we would like to do is to that the harmonics which are generated propagate at the same speed, the same phase velocity as the fundamental field. So in other words, we want the refractive index at the fundamental frequency to be equal to the refractive index at the harmonic frequency. Is it possible? Well, here I'm looking at the variation of the index over a broad range of frequencies. And we start with a laser in the infrared or visible. The refractive index is larger than 1. And we're generating harmonics in this extreme ultraviolet range where the refractive index is less than 1. So just looking at this, phase matching is not possible. Fortunately, we are actually ionizing a little bit the medium. Some electrons, they are driven away and they never come back. They are moving on this roller coaster forever. They leave, actually. And this contributes to a medium which is partially ionized. So if you look at the refractive index here at the fundamental frequency, you get an additional term to this due to this ionization, which lower the refractive index. And then you can see that it's possible to achieve phase matching. And this happens for a degree of ionization, which is typically a few %. So this means that there is a certain window of laser intensity for which this phenomenon is possible. You need high intensity to generate many harmonics, but not too high intensity to have the right degree of ionization. So this is a simple picture of how phase matching is achieved In reality, it's a little bit more complicated because you have to account for the influence of focusing of the light, leading to a phase shift, and also the influence of electron trajectory. The electron is carrying a phase on its trajectory, which is then transferred to the light field. So it's a little bit more complicated, but it's more or less you have the physics here. Now we are moving towards the end of the 90s. This is when the field really grew very much. In particular, you have several labs working with ultra-fast optics, being interested by this high-order harmonic generation, with the idea, oh, here is the new frontier. Maybe they are attosecond pulse. So you have really many labs starting in the field with very advanced laser systems, so pushing the field. So in particular, you have, this is where we start talking about few cycle laser fields with pulse duration less than 10 femtoseconds. So this is just a few cycle. Also with the help of the compression technique, for example, the hollow fiber technique. And this is where we started to really manipulate laser fields looking like this, where the carrier envelope phase, this is the phase difference between the maximum of the envelope and the maximum of the oscillation. So this also play a role, so we need to control that. So there is a really going back and forth between laser technology and progress in laser technology and this field of research. And this led to really a breakthrough in 2001 with both the measurement of attosecond pulses and the generation of attosecond light pulses, isolated attosecond pulse. Pulse measurement of attosecond pulses in a train of pulses was shown by Pierre Agostini in 2001. And I'm going to explain the technique that he used in a moment. And Ferencváros, using a very, very short light pulse to begin with, managed to generate a single attosecond pulse and to measure it using a technique called streaking, which is not exactly the same as the technique used by Pierre Agostini, but similar. Both measurements use a cross-correlation measurement in a gas, and it's based on laser-assisted photoionization of a gas. So I'm not going to describe both techniques, but I will describe the technique used by Pierre Agostini in connection with application of attosecond light pulse. What happens now, if I move a little bit rapidly, we're 20 years after, more than 20 years after this real breakthrough in the field, and well, we're continuing doing a lot of progress all the time in laser technology, and this is driving our field forward. First of all, we're starting to use other type of system, for example, the optical parametric chirp-pulse amplification system, which is represented here. It's nonlinear optics, and this really opened the possibilities for laser light. Suddenly, we can use different wavelengths, much more in the infrared, for example, or short pulse duration and tunable. Today, there is even an even new laser technology that I think is going to change completely the field, because it's very simple, it's very user-friendly, it's based on ytterbium, it's high average power, very high repetition rate. Now we talk about 100 kilohertz, so 100,000 hertz. And remember, we started with 0.1 hertz. So a huge difference what you can do with this laser system. And there are also new techniques to compress these pulses, which are a little bit long, using post-compression in a multipass cell. Huge progress in HAG metrology, what you can do, what you can achieve in high-order harmonics. For example, using longer wavelengths, you can get harmonics in the, not only in the XUV, but in the X-ray range, or soft X-ray range. And this is a beautiful result obtained by the group of Margaret Murnane, Henry Captain in Gila. You can also use multiple wavelengths. You can produce harmonics with different polarization states. So far, I have described harmonics produced by a laser which is linear polarized, and the harmonics are linear polarized, but you can use several wavelengths to get harmonics with different polarization states, and also harmonics with orbital angular momentum and structured light. This was the subject of a thesis defense this morning. I'm looking at the new doctor here. I don't know if he's here. Yes. And this is a very important result in this field by a group at Salamanca, Carlos Hernandez Garcia, and with pleasure will really push this field of producing harmonics with different polarization states and also structured light. And as I said, we have a new doctor. This is a very old photo of you. This is the only I could find in the internet. Sorry for that. But he got his degree, that's the idea. Okay, I'm going now to the last part of this talk, which is a little bit application. How do we use this pulse to study electron dynamics? And I'm going to focus on one process, which is photoionization. This is the photoelectric effect, where an atom absorbs light and an electron is emitted. This is the process that Einstein discovered theoretically in 1905, and this is actually why he got Nobel Prize later on. So I'm going to focus on this process. When Einstein studied this, he concentrated on the property of light, and this is where he had the intuition that the energy of light could be described by light quanta. I'm going to focus on the photoelectrons. You probably think of this photoelectron as a particle going away, and you can measure its energy or maybe its momentum, click. But we know that this electron is also a wave, so it's both a wave and a particle. And what we can do, which is new, is we can measure the wave properties of this photoelectron, or even quantum properties of the photoelectron. So this is what I'm going to tell you about. How do we do that? If we ionize our atom with our high-order harmonics, in the time domain, this is a train of attosecond pulses. So we ionize an atom. What do we see? We see electrons at different energies corresponding to absorption of the different harmonics. You don't get any temporal information, just spectral information. So this is not enough. We need a probe field. We need a fraction of the fundamental field. In the time domain, you have the optical wave, and the absorption of the fact that you add this probe field results in the possibility to have two photon ionization. So absorption of one harmonic plus a laser photon. leading to sideband peaks in the photoelectron spectrum. This sideband can also be reached by absorption of the next harmonic and then stimulated emission of a laser photon here. So suddenly we have a quantum interferometer. We have here two paths leading to the same final state, this sideband electron. Again, we're doing quantum mechanics. We add two amplitudes and then you square. So the signal that we are going to get depends on the relative phase between these two quantum paths. This path or this path. Now, it's an interferometric measurements. We would like to have something that varies in order to see fringes. And what we vary is the delay between this attosecond pulse train and then this probe field. This technique was first invented by Pierre Agostini and his group, and based on an idea by the group of Alfred Mackay in Paris. It's called rabbit reconstruction of attosecond beating by interference of two-photon transition. It's called rabbit because we follow the tradition of ultrafast optics to call the characterization techniques with animal names. That's why. How do we do that in practice? We need an optical interferometer, for example, a Mach-Zehnder interferometer, where in one arm you generate harmonics, you generate your attosecond pulse train, you remove the fundamental field here with a filter, and then in the other arm you have this probe field, and you can delay very accurately this probe field. And this interferometer is very accurate. This is where we have a lot of technology. It needs to be accurate on the typically 10, 20 attosecond time scale. Again, this is our tool. We focus this radiation in a chamber where we put some gas and we detect the electrons. In the results I will present, we collect actually all the electrons. It's called a magnetic battle spectrometer. This is an example of spectrum that we get. So what you see here is in color is the spectrum, so many peaks. And the vertical axis is the delay. So what you see are electrons due to absorption of the harmonics, but also you have these sideband peaks that very nicely oscillate. This is where the information is in the phase of this oscillation. And you see that this measurement is really in the attosecond timescale here. The difference between two peaks is half the laser period, 1.3 femtosecond. So this is kind of summary of what this technique allows us to do. We ionize a gas by absorption of this high order harmonics or attosecond pulse train. We create an electron wave packet. This is in blue. And then we characterize this attosecond electron wave packet by interferometry. Using these red photons, we can read not only the intensity of the wave packet, but also the phase of the wave packet or the phase variation of the wave packet. So the interferometric signal looks like this. Instead of talking about phase, we can talk about delay. And the delay that we measure actually is due to two contributions. One contribution is the delay, if you want, the pulse duration of the properties of the excitation pulse. And this is why this technique was first used to measure the pulse duration of attosecond pulses. And then you have a group delay due to ionization. And this is now the information that I want to get, the physics that I'm looking for. In reality, there is a third contribution, which is due to the measurement. But this contribution is small and can be calculated, so I'm not going to discuss that. Still, we have a problem. There are two unknown quantities. How can you measure these two quantities? Well, you can always do a difference. We can, maybe you can calculate this and determine this, and then you put another gas and you make the difference between the two measurements. So I'm going to show you an example of that. To finish on this, this is a kind of physical interpretation, and what is this delay due to ionization? It's actually a quantity which was first introduced by Wigner in 1955 as a derivative of the scattering phase in a scattering process. So here it's not scattering, it's photoionization. It's like half scattering. And the interpretation, I think it's simply the delay due to propagation of the electron in the potential. Let me show you an example. We look at xenon, and here it's a very old measurement showing the cross-section of ionization of xenon in the 4D shell. And it shows a broad resonance peaking at 100 eV. So now we want to do dynamics. We want to have a picture of this in the time domain. We want to see how does an electron is emitted out of the 4D shell. So on the right, you are in the time domain. The information that we have on the left is in the frequency domain. How can you go from time to frequency domain? You know the answer, Fourier transform. Can you do a Fourier transform? Well, we are missing information, the phase, or the phase variation, or the derivative of the phase, which is the group delay. This is what I'm talking about. And this is really what is new with our technique. We can now measure this group delay. And then we can go in the time domain. Let me show you an example of measurement in xenon. This is a 4D3 half electron. And this is this delay measurement over actually half this broad resonance. We see that it's positive and it's increasing, and actually it's quite long at threshold. And we can identify that this region here corresponds to this resonance, which has been called the giant dipole resonance, interpreted in terms of collective effects in the 4D shell, while we interpret this long delay of 100 or more attoseconds to the result of the spin-orbit interaction at threshold. And from this, we can go in the time domain and really describe the physics of photoionization with different trapping time for the electron. A short trapping time in this region here, much longer at threshold. So now I'm coming to the really last result that I want to show you. It's what we're doing now. We ask ourselves, but can we always talk about this photoelectron wave packet as a wave, almost like an optical wave with an amplitude and a phase? Maybe in some case, it's not coherent. It's only partially coherent, and we cannot describe the electron this way. So we need to do better. We need to characterize really the quantum state of the photoelectron. So here I'm going to use a little bit the language of quantum information. What I'm saying is that this photoelectron is not always a pure state. It can be a mixed state, and we would like to measure its density matrix. How can we do that? We propose here a method where we probe the wave packet using, this time, a bichromatic probe field, not only one color, but two colors. but otherwise very similar to actually rabbit. So here's the idea. We create a wave packet here with just one harmonic actually, and we probe this wave packet using this bichromatic radiation. So same idea, we create a sideband and we get information on this sideband. Just to explain a little bit better, if I split these XUV photons into two, so two different frequencies, you see that looking at the sideband, certain final energy. So I see appear now again these two quantum paths leading to the same final state. Two different quantum paths probing two energies of this photoelectron wave packet. So let's look at the interference of the sideband as a function of delay, and the contrast of this interference signal is going to tell us whether there is a well-defined phase relationship between these two energy states. So in other words, we're going to access the coherences of the density matrix by this technique. And similarly, the phase is going to tell us about the phase of this density matrix. So what I'm telling you here is called tomography, quantum tomography of the electron wave packet. And just to follow the habit of ultrafast optics again, we call this method Kraken. So now you have to use a little bit of Swedish to make this Kraken acronym appear. We need the Swedish again to have the K. And this is what it means. This is a Kraken measurement. So in order to do the tomography of the wave packet, we need to vary the frequency difference between, we need to vary omega 1, omega 2. And here are 6 measurements using different pairs of frequencies. And from this, we can recover the density matrix of the photoelectron. You have, so it's energy, energy, we are in the continuum. The diagonal is in this direction, and here we have our measurements leading to this subdiagonal by Fourier transform, subdiagonal of this density matrix. We make some optimization procedure. We use this procedure to fit this result, and we get this very nice round density matrix. This is obtained in helium. So what this means is that in helium we create a pure state. The corresponding purity is equal to, it's almost equal to 1. So in that case, we understand what is happening. Let's do the same experiment in argon. And here we see a density matrix which is elongated. It's typical of a mixed state. We lose coherence in this region, obviously. So what is the reason for this? Well, it's due to the spin-orbit interaction in argon. You can create argon ion in different spin-orbit states. So actually the electron distribution has 2 contributions. Again, in the language of quantum information, that means that when we photoionize argon, we create an entangled state between the ion and the electron. If these 2 distributions were not overlapping at all, this would be the maximal entanglement, because if you detect an electron here, you know that the state of the ion is 1/2. If you detect here, you know that it's 3/2. There is a small overlap region. If the electron has this energy here, then you don't know. Okay, so there is some loss of information. So we measure only the degree of freedom of the photoelectron. We measure reduced density matrix. The purity is 0.61. It's a little bit higher than what you can predict if there was maximal entanglement. So with that, I'm coming to the end of this talk. I would like to say that attosecond science is really very open at the moment with many applications in chemistry, condensed matter. There are some industrial applications. And now there is this very interesting interface with quantum information, not only for the photoelectron, as I showed you, but also for the light field, for the attosecond pulses. You can have attosecond pulses using high-order harmonic generation. You can do that at the ELI facilities in Europe. And you can also have attosecond pulses using free electron lasers. And this is really developing very, very rapidly at the moment. Just a month ago, I visited the LCLS in Stanford, and they say that half of the application now is with attosecond pulse. So it's really moving extremely rapidly. Very interesting. So with that, I just show this picture. This is for the young people here. If you happen to be a little bit lucky, that as I was, to be a little bit at the right place at the right time, and then to continue on this subject, maybe like 34 years afterwards, which is kind of long, you will find yourself in this room, which is the concert hall of Stockholm. Actually, it's next week. I will actually go next week. Next week is for the next Nobel Prize. And maybe you will receive a medal from the hands of His Majesty, the King of Sweden. And after the ceremony, which is very nice, there is a banquet. This is in the City Hall of Stockholm. There are like 1,300 participants. It's extremely formal. And maybe you will sit close to the King of Sweden. Only women can do that. But with that, I would like to say that this work is really, I would like to emphasize the importance of teamwork and collaboration in this field. This is a photo of my group in Lund. And here you have the senior people in the group or half senior working, and we are collaborating with theorists. Of course, we need some organization financing this research. I would like to really stress the importance of European collaboration. You can notice that the 3 Nobel laureates were European. And I think there is a reason for that. Is very early we have learned to work together in Europe through the Marie Curie networks, through Laser Lab Europe campaign in the different labs. So we have learned to exchange ideas, exchange students, and work together. I think that's been very important. And finally, I would like to thank you very much for today. I hope you have questions.
Yeah. Thank you very much. Very interesting talk. So I think it's time for questions. If you would like to make some questions in Spanish, there is no problem with this. We can translate. Okay? So don't be shy. Ask questions as you want. And also for the older people.
Yeah.
So is there any question there? Okay, so probably I can start. But
Yeah, there is one question here.
Hello, thank you for your conference here. I'd like to know what made you got interested into searching for attosecond pulses instead of any other field of physics. Thank you.
So your question is, why did I choose this field?
Yes.
Yeah. Well, I was interested by atomic physics. I had fantastic teachers in France in atomic physics, Claude Cohen-Tanuji. And so for me, interaction between light and matter was very interesting. So, and laser were fantastic things. and then I started my PhD on this, looking at multiple ionization in atoms. Very interesting. And then I could continue as a postdoc and then as a researcher. And then we say, oh, we look at light. Why not? And we saw these high harmonics. And then that was fascinating. So then I'm still working on high harmonics. So that's my answer. It's not really, oh, I want to generate attosecond pulse. No. It's, okay, I want to be in this field, and I got this possibility to do internship and then a PhD. And then, oh, it's interesting. And then you a little bit stumble on something which has, and this is what I say, it's a bit luck to find something which is new and interesting. Yeah.
More questions? Yeah.
So thank you very much, first of all. And how can you, or is it that you are making the state collapse of the electron when you measure it, or you can take it coupled and on its entangled state?
It's a very good question. Yes, the state collapse, of course, when we measure it, but we can go back to this phase information. It's not. I don't know how to explain that. What we get is a result of this interaction involving several colors, which it's an interferometric measurement, so we can recover the phase information. This is how we do that.
But once you do that, you destroy the state, right? Or at least you make it to the whatever you've measured.
I destroy the state, absolutely. So I get the electron on a detector. But this measurement allows us to go back in time. And actually, this I didn't show because this is in progress, but we can even determine, for example, the time scale for the entanglement in this. So we can really do new things thanks to this technique. Yeah.
Hi. So you said you were lucky enough to live this groundbreaking moment in optics or physics. So which one do you think that it's going to be the next groundbreaking moment? Maybe not in optics, but in physics.
I wish I knew the answer to that. I really don't know. I mean, there are, of course, in physics, there are things that we would like to understand. For example, the dark matter and these things. And there is, but I would like to say that probably the most exciting is something we have no idea about. This is my guess. So physics is very open. I think it's more open now than it was when I started, actually, so, which is fascinating. And optics is very cool. Yeah. Yeah.
No more questions? Yeah? Okay, I have a small question,
Yeah.
which is about the human part of the discovery. I mean,
Yeah.
I'm always wonder what you feel the first time that you saw this harmonic spectrum. If you knew which was the importance of this, if you believe your data, you have to repeat the experiment, or
Yeah.
what was?
I mean, of course, you have to repeat the experiments. Yeah, it was very strong. There was no doubt. It was not something small and lots of noise. It was very strong and really repeatable. Yeah, change laser, we see the same. So I remember this moment because it was so exciting because it was unexpected and it was very strong, really, really strong. And I had first it was new, and comes immediately the question, how can we understand that? And at that time, there were many theorists doing strong field physics, single atoms. But the part with phase matching was not studied, was not, I mean, there was really something to do for a young researcher, which was to develop this part and to put things together. So I felt that, oh, but this is something I can do. And it's open. So I had no idea about attosecond light pulse. This came later on, made the whole thing even more interesting. But no, I don't know. I had a kind of a researcher drive to simply try to understand better what we were observing.
Thank you for the talk. With this new science of attosecond, what would you really like to know that this could measure, for example? Is there something that you would like, either for you or for future physicists, to really find out with this?
That's a very good question. I can answer different ways, but I think one challenge is to what I told you about these measurements in atomic system. We need to do similar measurement in more complex systems, really to develop applications of attosecond light pulse. I think that's very important. I like very much the development towards quantum information. So try to understand in the time domain this physics, quantum physics. And then I think what I heard this morning to use a structured line to develop this harmonics with structured light is also very fascinating because it provides a means to act on matter in a very original way. So it's kind of growing in many directions. Yeah.
Hello, thank you for the presentation. I would like to ask if in the search of shorter and shorter lasers, is there a point where the Heisenberg uncertainty principle gets in the way of time and energy?
Is in the way. Well, I guess it's in the way all the time. We are not absolutely not violating Heisenberg principle. Sometimes we circumvent it a little bit. For example, when this is the whole idea of using this train of pulses instead of a single pulse, and it's again the going from time domain to the frequency domain. If you the spectrum corresponding to a single pulse is very broad, while the spectrum corresponding to a train of pulse is this high order frequency comb. So you gain by in the time domain, you repeat your measurements every attosecond pulse, correspond to the frequency domain to have much higher spectral resolution. So this is what I'm calling a way to circumvent a little bit Heisenberg principle. Yeah.
Hello. I was wondering, how did you know that you have won the Nobel Prize? Thank you.
You get a call from Stockholm, and for me, just 1 hour before the announcement to the world, so you don't have much time to react. And for me, it was actually during a lecture, so it was even more, let's say, complicated, because it was a lecture of 100 students, engineering physics, and I got the call during the break of the lecture. It's 2 hours. There is a small break in between. And in Stockholm, they wanted me to stay on the phone. And I told them it's impossible. I had 100 students waiting for me. And they say, okay, go back to your class, but you should not tell them anything. So I went back to the class, and I continued my lecture. I told them, okay, I have to leave 15 minutes before the end. This never happened to me. And I think at this point they guessed, so they tried to upload. And I told them, I haven't told you anything, which was really not the right thing to say. So this is the story of this. It was very special. But I continued my lecture half an hour. They helped me to write the right equation on the board. It was very tough, actually. But they were very nice. The following day, I also had a lecture. And this was also a very difficult lecture because I was so tired. But they came with a huge flower bouquet, and it was very nice. So they kind of remained for me, they belong to this Nobel Prize a little bit. It was very emotional. Yeah. So this is for the future here, Nobel Prize. Try to get the call when you are teaching. It's a bit special. And of course, the university loved it because it was promoting the teaching. So, yeah.
So, madam, there is one question online. So,
Okay.
I will, since we have many students today, what is the best advice you can give them for their future as scientists?
I would say choose a subject that you like. I think that's very important because being a scientist is really being a little bit passionate for a certain subject. And then be a little bit obstinate. Science, there will be ups and downs. There will be some people that will tell you, oh, stop doing that. Don't listen to them. So be a little bit obstinate, follow your heart. Yeah, that's my message.
There was another hand over here. No? Okay.
I have a little question, maybe of interest for the students. So, what would be the limitation of the shorter pulse that can be? Is there any limit?
I think the limit is very far away. So I think you can get shorter pulses. No problem, except of course for example, using these high harmonics, you can. We know how to make very long plateaus that would sustain this very short pulse, but the difficulty is to have all the frequency components approximately phase locked, approximately at the same time. So I think it's more technological than fundamental at the moment. The record I heard recently is 19 attosecond, which is very short. Yeah. And I think it's in Spain in addition, in Barcelona. Yeah.
So if there is no more question, I don't see any hand. Okay, so I think we shall thank very much, Angelica.